So what I want to start off with today is just is a brief review of some aspects of the topological string and the various gauge theories one can build in topological strings. So many people might have seen this before. So there's two types, two essential types. So they're called the A model and the B model. And in the simplest formulation, each has a worldsheet theory topological worldsheet theory with space-time X, which is a Calabi-Yau threefold. So we're going to focus mostly not on the worldsheet, but on the space-time, because when you're doing holography, you're interested in gauge theories and in supergravity theories. And also mostly focus on the B model. And like in any string theory, or like most string theories, there's both open strings and closed strings in the B model. So for a little while today, I want to focus on the space-time theory for B model open strings. And this will lead us to some kind of fun gauge theories we can play with and analyze holograph. So to do this, we need to know what is a brane in the B model. The fancy definition B brane is a coherent sheaf on X. But actually, you don't particularly need to know that, know what a coherent sheaf is, because really the B branes you will ever really see concretely are pretty simple. So concretely, so one class of B branes are space-filling B branes are going to be holomorphic bundles. You can also have B branes which are not space-filling but live on some smaller subspace. We'll also have the other branes will typically live on some complex submanifold. So the kind of thing you might look at is you take some complex submanifolds cut out by the zero locus of some holomorphic functions, and you might have a vector bundle on that. Okay, so we'd like to understand the open string field theories, which is going to be some gauge theory. And if it's a space-filling brane, it's going to be a gauge theory on X. And if it's a brane living on some submanifold, it's going to be a gauge theory where the fields live on that submanifold. So there's some very nice axiomatics of what is an open string field theory. It's in a paper of Witten from 86 or so. So Witten tells us that to give an open string field theory, we should give a cochain complex of open string states so it's graded by some dose number, and Q is the BRST operator on the world sheet. A multiplication map should be an associative multiplication. So this comes from thinking about some kind of open strings like that. I've labeled all these boundary pieces by the brane, which all the open strings end. Here I take a state for this brane, a state for the open string stretched between this brane and itself, a similar state here. I can multiply them using this worldsheet diagram. And what properties must this satisfy? Well, it's associative. From the topological point of view, associativity is obvious. Let me just quickly draw the picture. I can cut it here. Or I can cut it here, and I will get the same answer. So the fact that you get the same answer tells us that this multiplication should be associative. And this should also play nicely with the BRST differential. So Q alpha 1, alpha 2, plus or minus so this is something about how the BRST operator acts on each piece. And the final piece of data is a map, which I'll write as the trace in A, which goes from A in degree 3. So this map is associated to this worldsheet picture. I have an open string. An open string, and I cap it off with this brane. I should get a linear operator where I put an open string state there, and I get nothing there, just by the axiomatics of a topological field. And what this is supposed to satisfy is the trace of a supercommutator vanishes, and the trace of the image of the BRST differential vanishes. Let me switch these around. Yeah, so I really like this picture, and it's certainly a universal picture for any kind of topological strings. We can always get something like this, although sometimes this might be some A-infinity algebra, which is a bit more. Witten also shows that it arises in the physical string, although that's more common.
Sir, why do you have A cubed in trace?
Not A cubed, A in degree 3. Because A is a cochain complex.
Oh, okay.
So you want to pick out the cochains of degree 3 and get a number. And the reason it's 3 is because the dimension of moduli space is 3g minus 3. So this is to cancel some ghost number anomaly. So in a minute, I'll give you some good examples of this kind of open string the solutions of these axiomatics. But first I want to explain how to, given a solution to these set of axioms, how you get a gauge theory. So this is also in Witten's paper. So in open string algebra, I'll give you a gauge theory. So for this, we will assume that this algebra lives in degrees 0, 1, 2, and 3. I mean, well, you can generalize that, but then we'll get a higher gauge theory. It's more general. So how do we get the gauge theory? So the fields are elements, say, alpha in A1 tensored with GLN. So the Lagrangian is half trace A of alpha times Q alpha. Here we're using the multiplication in the algebra, which is part of the data. I'm not calling it M, I'm just writing it by juxtaposition. So 1/3 trace of alpha cubed. So you might recognize this as a Chern-Simons type Lagrangian. And the gauge symmetry this is generated by so I'll call it C in A0 tensor GLN, and the variation of alpha is QC. So your field varies by this formula, which is the standard formula for an infinitesimal gauge transformation. Okay. This is just a little bit of formalism for how to build gauge theories. And the idea is that if you do the path integral, then your Feynman diagrams if you write them in double line notation, these are nothing but the world sheet. Of the topological string. So for instance, we see here that the multiplication on A is given by this little piece of a world sheet where two strings merge. So that multiplication appears in this vertex. So the vertex is literally three strings merging. The kinetic term is a bit more mysterious, but intuitively, we build Feynman diagrams, we're gluing strings together to form an arbitrary world sheet. Okay, so let's give some examples of solutions to these axioms. So I'll start with this example of a space-filling brane in the B model. I take X, Fabio threefold, and we take a space-filling brane. Then A, in this case, is the Dolbeault complex of X. So does everybody know what this is? Or should I explain? I mean, in coordinates. So in local coordinates, this looks like functions on X adjoin dz bar I. These are of Gauss number 1. So it's just like a truncation of the de Rham complex where I don't include any of the holomorphic directions. So Q is the d bar operator, which locally looks like in coordinates some dz bar I del z bar I. So you notice that, for example, the kernel of this operator, things in Gauss number 0 in the kernel of this are precisely holomorphic functions. So it's related to the holomorphic geometry of X. The multiplication is just the wedge product. And the trace on A must take a 0-3 form. What it does is it sends alpha to the integral over x of omega x wedge alpha, where omega x is the holomorphic volume form. On x, so locally, it's like dz1, dz2, dz3. So for everything else, we didn't use the fact that it's Claviau. It's only to write down this trace map that we needed to just be Claviau. Okay, so let's follow Witten's prescription and try to calculate what is the open string gauge theory. Well, the fundamental fields are going to be alpha, which is a 0, 1 form in X, tensor GLN. So this looks like it should be a gauge field. But it doesn't have, this is 6 real dimensions. This field only has 3 components. So it's like half of a gauge field. So, partial gauge field. So what it does is it allows us to differentiate. This is the kind of, a gauge field allows us to do parallel transport and differentiation. This allows us to differentiate in the z-bar directions. So we like have a covariant derivative in the z-bar I direction would be del z-bar I plus the corresponding component of this. Make sense? Yeah. So for Blackboard use, now what's the Lagrangian? Is half integral over x trace So this Lagrangian is a Lagrangian for holomorphic Chern-Simons. And I won't write down the formula, but the variation of a field under the gauge transformations is the usual variation of a gauge field, except that we, in the usual gauge field variation, we might pick up a 1, 0 component. We just throw those away. So maybe you can write that out. So variation of alpha is sum dz bar I del z bar I c plus alpha c. So usual variation, except only in the dz bar directions. Okay. So we've seen. So now this is in. It's discussed in a paper of Witten from about 92 about Chern-Simons theory in the topological string. So we see that the holomorphic Chern-Simons theory appears as the theory living on a space-filling brane in the topological B model. So I want to give a few more examples. And as I said, our goal is to understand the theory living on a brane which is not space-filling, and then understand that theory in the large n-limit holograph. But to get there, really, it's kind of helpful to do some more simple examples. Okay. Unless there's any questions? Yeah.
Typically, the Chern-Simons action is not invariant under the gauge transformation, as in there's a filter. Is the same true here?
Yeah. So the Chern-Simons action is not invariant under large gauge transformations. It is invariant under gauge transformations which live in a neighborhood of the identity. So this Lagrangian is perfectly fine as a perturbative object. But the non-perturbative, nobody has any idea about the non-perturbative version of Chern-Simons. Okay, so the next example, suppose we take X to be the cotangent bundle of M, and we do the A model. So then branes are Lagrangian submanifolds in particular, they're middle dimensional, they're of dimension 3. And suppose we take our brane to be M. The zero section. Then the open string algebra is going to be the algebra of forms on M. Q is a de Rham operator. The multiplication is a wedge product, and the trace on A from takes the 3 form to C is the integral over M of alpha. This is a very simple example, and was also discussed in that paper of Witten I mentioned. Okay, so what's the corresponding field theory? Fundamental field is now just a one form in M, coefficients in GLN, and the action is the usual Chern-Simons Lagrangian. So we find ordinary Chern-Simons. So there was an issue raised about Chern-Simons theory not being gauge invariant. That issue, even though this is ordinary Chern-Simons, that issue is actually relevant here. Because if we keep track of the string coupling constant, it appears there, 1 over the string coupling constant. So the string coupling constant is not an integer. So this is only well-defined in perturbation theory. Okay, any other questions? Okay, so let's move on to the kind of example that's going to be more relevant for us. So we're going to do the B model on a Calabi-Yau threefold X, which is a rank 2 vector bundle V over a Riemann surface. So for this to be Calabi-Yau, we need wedge 2 of V equal to the canonical bundle of sigma. And then, because the volume form will transform as an element of wedge 2 V star tensored with the canonical bundle of sigma. That will be a trivial bundle, which is what you need for it to be Calabi-Yau. So an example, e.g., x might be C2 times an elliptic curve, because an elliptic curve has trivial canonical bundle, or x is the total space of O minus 1 plus O minus 1 over CP1. Because the canonical bundle of CP1 is O minus 2, so this thing is Calabi. And this is sometimes called, this example here is sometimes called the resolved conifold. Okay, questions? Is that understandable? Okay, so the brane we're going to consider a brane which wraps sigma. So there are some rules for computing these open string algebras. They're rules using techniques of homological algebra. So what you're supposed to do is compute something called the X groups of the coherent sheaf. Now, I'm not going to assume anybody knows how to do that, so I can just tell you the answer. I'm just saying that just to point out this can all be made very systematic. So it's the Dolbeault complex of sigma with coefficients in the exterior algebra of V. So it's always going to be the exterior algebra of the normal bundle that will appear. So what does this mean in coordinates? This looks like functions on sigma adjoin three odd variables, dz bar I, epsilon 1, epsilon 2, where the epsilon I are odd. The differential is the d bar operator, which in coordinates is so this operator doesn't touch the epsilons, it only touches this odd variable. So epsilon 1, epsilon 2 are locally defined sections of the vector bundle V. So when I globalize, they become sections of V. And the algebra structure is just given by wedge product. So in local coordinates, that means we just have our usual bosonic variables, which are functions on our surface, and three fermionic variables, like which anti-commute. The trace map, well, that's going to go from my algebra in degree 3, which in this case, well, this goes as far, this index here can be either 0 or 1. This index can be 0, 1, or 2. So to be in 3, this has to be a 0, 1 form with coefficients in wedge 2. That's omega 0, 1, sigma, wedge 2v. And well, we assume that wedge 2 is the same as the canonical bundle, meaning it transforms like dz. So that's the same as omega 1, 1 of sigma. And then the trace map is just integration. So in local coordinates, for example, we can assume that epsilon 1 and epsilon 2 transform as sections of square root of k, like they transform like dz to the half. So their product transforms as dz. So that means I can integrate dz bar epsilon 1, epsilon 2. That's the thing I can integrate. Okay, questions? Okay, so let's analyze this example a little more. So what are the fields of the field theory? Well, they're going to be my algebra degree 1 tensor GLN, which is omega 0, 1 sigma plus omega 0, 0 sigma coefficients in V. So I have two kinds of fields. My fields are like A in here, which is like a gauge field. And Z in here, which is a doublet of scalars. So I say it's a gauge field, but in the same sense as we mentioned earlier, it only allows me to differentiate in half of the directions. So it's like a partial gauge field. And well, what's the Lagrangian? What's the gauge symmetry first? The variation of my gauge field is just given by the usual formula. And the Lagrangian well, this guy has two components, and the Lagrangian, this integral map, is obtained by wedging them together. So the Lagrangian looks like this. Make sense?
Do you have Z1 and Z2, for example?
Yes, maybe that's better if I wrote like that. We assume that V is like 2 copies of k to the half. Then this could be Z1, Z2. And then I write this as Z1, Z2, Z1, Z2, and Z2. That's clear. Okay, so now we've come to the conclusion that I put a brain on wrapping a Riemann surface. And this is like a general local model for a Clavier threefold in the neighborhood of a surface. I put a brain wrapping a Riemann surface in a Clavier threefold, and then the theory on the brain. It has 2 scalars, which tell me about the motion in the normal direction, and a gauge field. And the Lagrangian, this term is something called, some people call this a system of symplectic bosons. So what we're left with is a system of gauged symplectic bosons. So Z1, Z2 are adjoint valued symplectic bosons, and these are gauged. So the precise form of gauging will be BRST reduction. Okay, so let's pause here and make an observation which leads us to conclude that this might be an interesting system to study holographically. Following observation. So this system is precisely a BPS part of n equals 4 super Young Mills. So there's a lovely paper by Chris Beam. That's 5 authors. I can't remember all their names. Sorry. Beam. What's it?
Van Reeves.
Yes. Van Polars or something?
Yeah. Pillars.
Pillars, yes.
One more person.
Yes. I knew working here. Yeah. So they show that any 4-dimensional theory with n equals 2 superconformal symmetry, there's some kind of localization where you can turn it into a 2D theory, 2D chiral theory. And if I start with n equals 4 Yang-Mills and I do this localization, this is the 2D chiral theory, I think. So of course, we know it's fun to study n equals 4 Yang-Mills holographically. This is a piece of n equals 4 Yang-Mills, so we can ask if we can study this theory holographically instead. So getting to that is going to be one of the goals I want to explain. Let's see. I think I want to do one more example. No, I think this is okay for now. Any questions? Yeah.
So here you have a special B model that just looks like a vector bundle over some Riemann surface.
Yes.
And you get something interesting on the Riemann surface. So there's some Lie algebra data that define the B model. Do you know what the data are here and what is the corresponding operation between them? Is there some correspondence between those?
What kind of? I'm not quite sure I follow.
So basically, this algebra with the Q operator, etc.
Yes.
There's just some Lie algebra that defines this on the whole thing.
Yes.
And then there should be something that defines the theory on the sigma model. And the question was if you know what this other thing is, if it's also a Lie algebra or what it is, and if there's some well-defined sort of correspondence between those two objects.
I'm not quite sure I totally follow. I mean, this like open string algebra thing. That's just defined by taking the x of the structure sheaf of the curve. Mm-hmm. It's not. Let's see. I mean, are you asking if you can recover the Calabi-Yau threefold from this theory?
No, what I'm asking is if I can do some sort of like operation on the Lie algebraic level, some sort of like a reduction or something, and get precisely the data that I need to construct this theory.
Well, I don't know. I don't think you really need Lie algebroids. I mean, it's just built from this submanifold, right? Lie algebroids are more like quotients.
So you're saying I just restrict that to the submanifold and
yeah, you just like take this structure sheaf and look in your algebraic geometry book how to compute the x's and find this. Okay, so So we have a couple of things we need to discuss before we get to something interesting. We need to, can we explicitly describe the algebra of operators of this theory? So the way to do that is to do BRST reduction. And we also need to understand the back reaction. To do that, we need to understand what does the closed string B model look like. So I think that maybe next time we can look at this example and study its BRST reduction. This is a it's a fun, concrete thing. If you like vertex algebras, that's a good thing to do.
You mean the back reaction to the brain on the Columbia?
Exactly, yeah. Mm-hmm. But today I want to just introduce the closed string states of the B model, which we haven't touched at all. So this was, the closed string B model was developed in a nice paper by Brzezinski, Shigoti, Iguri, and Vafa sometime in the mid-90s, 96 maybe. So it's somewhat more complicated. So for us, the closed string states will just be a Lie algebra. Well, let me see. I'll write down the closed string field. Closed. So you can derive the space of closed string states by studying the world sheet. So I'm not going to go through that. I'm just going to again tell you the answer. But the way to think of it is to think of, you can kind of guess what it must be, what some of the ingredients must be. So in ordinary string theory, we know that the closed string states include a graviton. Now here, there's no reason for having, the metric does not appear anywhere. This only depends on the complex structure. So the replacement for a graviton is not a metric tensor, but the tensor describing deformations of complex structure. So the fundamental field is what's called a Beltrami differential. Say beta so it's a 0-1 form with values in the tangent bundle, so that locally you can write beta as some beta I bar j d z bar I bar del z j. This kind of thing. So its components, it has these components. So it's a mixture of dz bars and derivative in the z direction. So why does this describe infinitesimal deformations of the geometry? Well, the reason is that this is the thing which will a tensor like this will allow you to change what it means to be a holomorphic function. So such a beta forms a complex structure by saying that d bar, which looks like some dz bar I d by dz bar I, gets sent to d bar plus some so we add on this term. So before the deformation, a function is holomorphic f is holomorphic if locally dz bar I f is 0, so that it doesn't have any dependence on z bar. So now this, once we deform, this gets changed to dz bar I f plus beta ij sum over j dz j f is 0. So the equation of being holomorphic is modified in this way. So if it's a good deformation, what you can do is solve this equation to find 3 independent holomorphic functions locally. Those will be your new holomorphic coordinates. Then you'll patch them together to get your new complex manifold. Now, annoyingly, this, if I take a random beta, this equation maybe doesn't have any solutions. So what we need to do, well, there's going to be some constraints in beta, which will follow from the equations of motion of the theory, which imply that actually there are solutions. So let me call this deformed d bar operator d bar sub beta. So there's a condition which guarantees there exist solutions. So this is like a standard integrability condition for differential equations, that d bar beta squared is 0. Which you can write out more explicitly as d z bar k epsilon I k beta I j plus beta something like this. This kind of thing. There's some factors and maybe indices are slightly messed up. But so this term would be saying that the d bar of this is 0, will be the linearized equation. But actually the linearized equation gets a quadratic correction, looks like this. Where it involves differentiating one beta in the holomorphic direction. Okay, so let's see. I'm going to maybe explain one more thing and then we can stop, and next time I'll move on to discuss the action, and we'll see this a little more. But, actually, I mean, this story about Kodaira's theory of deformation of complex structures is a kind of a fun thing to understand anyway. So there's another constraint too, right? So even if, okay, suppose we have solved this condition, and we know that this satisfies the integrability constraint, which guarantees there are enough holomorphic functions. How do we know the resulting manifold is still Calabi-Yau? Because maybe there's enough holomorphic functions, but there might no longer be a holomorphic volume form. So to ensure the new manifold is Calabi-Yau, we need that something kind of divergence of beta vanishes. Where this divergence some So we take beta ij and differentiate in the zj direction. So the reason this is called a divergence is that suppose beta was a vector field. Then I wouldn't if beta was a vector field, I wouldn't have this upper index, and I would be doing literally the divergence of a vector field. But now this is a vector field with an additional index coupled to the dz bars, so I'm just doing the divergence in the vector field part. Okay, let's see. So next time we will discuss more on, more about a little more on the closed string B model. Okay, any questions?
So should we see the demand of the target space is Calabi-Yau is coming from a consistency condition for the string propagation?
Yes.
So it's like the physical string, that there's some Ricci flatness or something.
Let's see. No, so in the physical string, the Ricci flatness comes from the equations of motion of the string field theory.
Right.
So here, the equations of motion of the string field theory is this equation, which tells me I have an integrable complex structure. So slightly annoyingly, the way this theory is set up, this condition is just imposed by hand.
I see.
So, which is extremely annoying because it's a differential equation and it's very difficult. It's a bit troublesome to impose a priori that your field satisfies a differential equation. But that's what one does here.
So it's to be seen as taken as part of the definition of the theory.
Yes. Like the fundamental field will be some beta satisfying this equation. And then with a Lagrangian, its variation implies this equation.
Actually, there's a paper describing explicitly the deformation of Ricci flat matrix by Xiaofeng and Yao. They wrote down the deformation of Ricci flat matrix explicitly for these equations.
Oh,
Not this is only for complex structure, but also the flat matrix, the Ricci flat matrix. Also have the equations explicitly for that.
equations of this kind of form?
Matrix. Similar, but it's more complicated.
Mm-hmm.
Xiaofeng and Yao.
Yeah, I'll have this.